In this video, we will discuss confidence intervals for populations when the standard deviation is unknown. So our previous lesson covered confidence intervals when the standard deviation is known. This video will be different. This will be when the standard deviation is unknown and will follow a different procedure. So remember, in upcoming exams, these types of problems will be mixed together, and it will be up to you based on the wording of the problem to identify, okay, is this a case where the standard deviation is known? If so, I do the process outlined in the previous video. Or if the standard deviation is unknown, I'm going to follow the process here. So as you work through these, once you finish this video along with the previous video, I would encourage you to look back at the different phrasings and make sure you're comfortable when which process is used. Now, it turns out in everyday life, it's more common that the standard deviation is unknown. So when we don't know the value of the standard deviation, our population, this is a population standard deviation, we can replace it with the sampled standard deviation, S. Now, the standard deviation S is only for our sampled. It's not the entire population standard deviation. In this case, we use a distribution called the student's T distribution. Now, here are some properties of the student's T distribution. First, it is symmetric, so we have symmetry, and there is only one mode. However, it is more spread out than the standard normal distribution, so it's not standard normal. But if we increase something called the degrees of freedom, the student's T distribution does become closer to the standard normal curve. There are many different student T distributions. The distributions are distinguishable based on something called the degrees of freedom. Now, the degrees of freedom can be found by taking the sample size in and then subtracting 1 from it. So the degrees of freedom is just 1 less than the sample size. Now, when the population standard deviation is not used, instead of the notation for our critical value from last section, we instead use the notation T subscript alpha over 2. And not only do we use different notation, in this case, in our previous lesson, whenever we knew the standard deviation, we used our normal distribution chart to find the critical value. However, whenever the standard deviation is not known, we have to do a new table called the critical values for students' T distribution, which is given on the next page of our notes and also linked in our course. Now, we're about to look at that page, but let's just take a few notes first. The largest number of degrees of freedom included in the table is 200. But since it maxes out at 200, and it also doesn't include every value up to 200, we have two questions. What if the number of degrees of freedom isn't in the table? Well, if the degrees of freedom is less than 200 and not in the table, then you use the next smaller degrees of freedom that appears in the table. If instead the number of degrees of freedom is more than 200, you just use the z value found in the last row. Now let's take a look at this chart, which is what we'll use to find the critical value when the standard deviation is unknown. This is what the chart looks like as a whole. I encourage you to print this out either from our note packet, it is embedded within our note packet, or from the individual file that is in our online course. So print this out, have it ready as you go through both the homework and the upcoming exam. And let's zoom in so we can see how to read it. So first, big details. Do you see this left column? It might be hard to read, but this says degrees of freedom, and it lists values 1 through 10, 1 through 20, 1 through, it looks like up to 40, and then from 40 it jumps to 50, 60, 80, 100, 200. Okay, this here is the z-score that we're given, so all of these are z-scores. And the way we would read the table is it corresponds to two things: the degrees of freedom and the area right of the tail, which is corresponding to the confidence level here. So if we had a 98% confidence level, and that's what you can see I've highlighted at the bottom of the screen here, and we had a sample size of 34, that would be a degrees of freedom, one less than that. So I would first look at the column that corresponds to a confidence level of 98%, which corresponds to 0.01 area to the right in tail. And of all these values, first I need to write down the degrees of freedom would be 33, because it's one less. Of all these values that you see boxed here, I would select the one that corresponds to 33. Seeing where this row and column intersect, we would get the z-score of 2.445. Now this is just a general overview of how this chart works. This is zoomed in so you can see a bit easier. And we're about to do many such examples, so we'll have time to practice this. Now one thing to note before we go forward is since the critical value for our standard deviation unknown depends on both the confidence level and the degrees of freedom, we will usually have to calculate it anew for each problem. We're not going to be able to do like we did in our last lesson of have a list of a lot of known ones, because it turned out if it was a normal distribution and you had a 90% confidence level, there was one specific z-score attributed to that. Here, since it depends on two things, the confidence level and the degrees of freedom, we'll have to calculate it anew each time. So in our first example, it says find the critical value here just by the notation t of alpha, or t subscript alpha over 2. I know that I'm dealing with this new chart that we use when the standard deviation is unknown, so pay attention to that context clues. T subscript alpha over 2 versus z subscript of alpha over 2. And here it says we have a 90% confidence level, and our sample size is 6. Now from the sample size, before I forget, because this would be my most common error, I'm going to say the degrees of freedom is not 6, but instead it is 1 less than 6. So I could write 6 minus 1, or we know that to be 5. So I'm interested in the z-score that corresponds to a confidence level of 90 and a z-score of 5. Now let's talk about one way you can use the chart. Remember 90%, remember degrees of freedom 5. Do you see here in the bottom part of the chart, we've got the confidence levels listed out? So you can read the chart in one of two ways. You could either, from the top of the chart, look at the area to the right of the tail, but that would involve a small calculation, drawing the chart and then representing it based on how much is in the middle, how much is to the left and right, shared symmetrically. But I think what would be easier is to come here and say, okay, if we're interested in a 90% confidence level, that would include this entire column, and you kind of visually highlight it. If it's on your paper, you can put two pieces of paper next to it to kind of cover up everything else except that. So this entire column is for the 90% confidence level. Okay, my degrees of freedom is 5. I know that's a row value because degrees of freedom are from this row. I visualize where they intersect, and we see that would give me a z-score of 2.015. So that's one way you could read the chart. Another way, although you'd get the same answer, but I think it would take a bit longer, this is maybe not the preferred method, is we would trace out our symmetric and unimodal distribution. We know we're enclosing 90% in the middle. That leaves me 10% left over, so that's 5% on each side. 5% turns into an area, move the decimal place over twice, and we get a 0.005 to the left and 0.005 to the right in terms of area. Now looking back at the chart, we see the top portion is area right of the tail. Well, our area to the right of the tail is 0.05, so that would give us this exact same column. So whether you like to find the column based on the confidence level percentage or the area to the right, realize they're the same thing. You might prefer one way or the other. Go with whichever method makes most sense to you. So next, let's calculate this one together, and then I'll ask you all to pause and attempt the final one on your own. But we'll go through this together one more time. So a 98% confidence level with a sample size of 12. Now, before we go to the chart, I can't use 12 I've got to find my new degree of freedom. Degrees of freedom. It is 12 minus 1, which is 11. So I'm going to be looking for the column of 98% confidence and cross that with the row degrees of freedom 11. Looking in the bottom, I find 98% here, degree of freedom 11. We zoom in and see the score is 2.718. Now I'd encourage you on this last example, level 99% with a sample size of 10, right now pause the video and attempt this on your own, unpause to check your work. Okay, so we've got our confidence level 99%. Once we get the sample size, we immediately find the degrees of freedom so we don't make a mistake. It's always 1 less than the sample size, so 10 minus 1 is 9. So I'm going to be looking for when the 99% column intersects the 9 row. So here I've got my 99% column confidence level. Okay, my row for degrees of freedom 9. We see where they intersect, and that would give me a critical value, or z-score of 3.250. So in our next example, it says a sample size of 22 is drawn from a normal population. Find the critical value, T alpha, subscript alpha over 2. So this tells us we use our new chart. Needed to construct a 90% confidence interval. So think, what would your degrees of freedom be here? Well, if the sample size is 22, that's 22 less 1, or 21 degrees of freedom, 90% confidence. So visualize where that critical value would come from. We'd get the 90% confidence column along with the 21 degrees of freedom. Zooming in, we see our critical value would be 1.721. Now, if the sample size were instead 15, which would lead to a degrees of freedom of 14, would the critical value be smaller or larger? We'll be able to answer this question if we just look at the chart. So remember, our new degrees of freedom is 14. So looking here, we see for degrees of freedom 14, we intersect and we get this 1.761, which, comparing this to the original, we see it would indeed give a larger critical value. Now here's our steps for constructing a confidence interval when the standard deviation is unknown. So it says, in order to construct a confidence interval using the student's t-distribution, the following must occur. First, we need to verify, do we have a simple random sample? Then, once we verified that, we need to know, is either our sample large, or if the sample is not large, is the population approximately normal? And what is our cutoff for a large population? The large population is greater than 30. So whenever you begin these problems, if the standard deviation is unknown, check first, is it a simple random sample? Then do we either have a sample size larger than 30, or if it's not larger than 30, are we drawn from a normal population? Now if both of those check out, then our steps are: first, compute the sample mean if it's not given, and the sample standard deviation, S, if they're not already given. Then 2, find the number of degrees of freedom. Remember that sample size minus 1. And then using our chart, the critical value that corresponds to the degrees of freedom and the confidence level listed. Next, compute the standard error. And then find the margin of error by multiplying the standard error and the critical value together. Then the confidence, as before, is sample mean minus margin of error between our mu's, sample mean plus margin of error. Now you have a rounding note. If you're given the sample mean, then round your final result to the same number of decimal places that were given in the sample mean. Okay. A sample size of 44, so we see our 44 is greater than the 30 cutoff, so we're good there. Has a sample mean of 56.1. I notice that it's to 1 decimal place, so all my subsequent calculations based on my rounding note will also be to 1 decimal place. sample standard deviation of 9.1, construct a 98% confidence interval for the population mean. Now I know that's going to end up being x bar minus margin of error. It's between our mu and x bar plus margin of error. I'm going to abbreviate it there. So in order to answer this question, I know the x bar is 56.9. I need to know what my margin of error is that I both add and subtract from 56.9. Let's find that off to the side. Margin of error is the critical value that corresponds to the value times my standard deviation, standard error, over the square root of the population. So here this is 9.1 divided by the square root of 44. Now my critical value, the critical value here will come from the fact that I had 98% confidence level with a degrees of freedom of 1 less than our sample size of 44, so that's 43, because that's our 44 minus 1. So now I just need to go to the chart with these two details in mind. My degrees of freedom is 43, my confidence level is 98. Let's find the critical value that would go here. So I've recorded that we're looking at a confidence level of 98%, 43 degrees of freedom. So we look at our confidence levels and we see here is our 98% confidence level. We highlight that column along with our degrees of freedom of 43. Now notice our rows jump from 40 to 50. So we don't have 43 mentioned, but the rule is you pick the last listed value. So we'd go to 40 as our estimate. So I would highlight this row, see where they intersect, and that's at 2.423 as our critical value. So we take the critical value times the standard error, and when we round this to get our margin of error, it's going to be to 1 decimal place because that's how the mean was given. So when we calculate it, we get this value rounded to 1 decimal place will be 3.3. Now that is my margin of error. So we replace that in our confidence interval formula. Simplify both sides, type these into the calculator, and we get 56.9 minus the margin of error 3.3 gives me the value 53.6. Now add the margin of error to the mean of 56.9, and we get a value 60.2. And that is our confidence interval about the mean. Now the next question is, if the sample size were 30, so 30 instead of 44, would the confidence interval be narrower or wider? Now for these types of questions, I think it's easier just to calculate it and compare. So think, where would the sample size change things? Well, one, it would change things here because the sample size is part of the standard error. So that would become 30 instead of 40. But it would also change things here because our sample size of 30 would give us a different degrees of freedom. This would give us a new degree of freedom of 29, which would give us a different critical value. Looking at the chart, the new critical value would be, we would instead have the degrees of freedom being 29, and our new critical value is 2.462. Okay, so they're asking if it's narrow or wider. We're just going to recalculate. This is critical value times the standard deviation for the population of 9.1 divided by my new sample size of 30 in square root. We round that to 1 decimal place, and we get 4.0 when rounded. Now compare this margin of error, 4, to the previous margin of error, 3.3. This would give you a wider confidence interval because it would take farther from the left and farther from the right. So we can answer this would be wider. So in these problems where it says, if this changed, what would happen? Remember, you've always got the ability to recalculate based on the new information. Just make sure you figure out all the places it would change things, and then compare to the original value to get your answer. Now it says, in a sample of 77 children, as I'm reading, I'm writing down key detail, sample size is 77. The mean age at which they begin to combine words, this is our sample's mean, is 16.51, so X bar is 16.51. And the sample standard deviation, because it's still within that beginning sentence, is 9.59. Now remember, when it deals with the sample, we use S. When it deals with the population at large, we use sigma. Now it says construct a 95% confidence interval for the mean age at which children begin to combine words. I know for the confidence interval, it's going to be X bar minus my margin of error. If you'll allow me to abbreviate it like that so we can write a little more efficiently. Now we happen to already know X bar. That's 16.51, so that doesn't need to be found. And of course, this should be a plus there. But I do need to find the margin of error in order to complete the problem. So off to the side, let's find our margin of error. We know that is, in words, our critical value times our standard error. Okay. Now the critical value we find from the chart, the standard error is a standard deviation of the sample divided by the square root of the sample size. So for us, we can fill in a few details here. Our sample size is 77, and our sample standard deviation is 9.59. So we filled in the details we can right off the bat. Now to find the critical value, we know that depends on the 95% and our degrees of freedom. Our degrees of freedom is 1 less than the population size, or the sample size, so 77 minus 1, 76. And now we need to reference our chart. It's 95% confidence, degrees of freedom 76. Why don't you pause the video and find the critical value on your own, unpause to check your work. So I look for my column for 95%, and we see that that's here. Okay, degrees of freedom is 76. Looking at my degrees of freedom rows, I see I have between 60 and 80 would be 76, but based on the rules, if the value doesn't appear in the chart, you choose the previous listed value. So if I'm looking for 76, I would choose 60. That was what came before it. We see where that intersects, and we get a critical value in this case of exactly 2.000. So that's our 2.000. And now we type it in the calculator. Now looking at our sample mean, how many decimals should you expect this to round to? Okay, so for our confidence interval problems, if given the sample mean, you round to that many decimal places. 2 decimal places were given, so I'm going to round to 2. And this would round to 2.19 when rounded to 2 decimal places. That is my margin of error. Now the margin of error is then subtracted from the mean and added to the sample mean to get my confidence interval. So putting this all together, 16.51 minus the margin of error. Our population mean is between these two values, 16.51 plus the margin of error. Now we're going to see what that would be. 16.51 minus 2.19, 14.32. 16.51 plus 2.19, 18.70. And that would be our confidence interval that we were asked to find. So remember, whenever you're asked to find the confidence interval, if you've got the sample mean, then you just have to find the margin of error that you would then alternatively subtract from the mean and add to the mean. The margin of error is the critical value times the standard error. Standard error is the standard deviation for the sample here, since we're with the standard deviation unknown, divided by the square root of the sample size. critical value in this case, since the standard deviation is unknown, comes from both the fact that we have a 95% confidence interval and a degrees of freedom of 76. Okay, it says, if a sample of 50 children had been studied, would you expect the confidence interval to be wider or narrower than what was constructed in Part A? Now, we've done an example kind of like this before. Think what the change of 50 children instead of 77 would affect in terms of our margin of error calculation. It would affect both this, because instead of the square root of 77, we'd have square root of 50, and it would also affect the critical value, because the sample size directly corresponds to the degrees of freedom. And we know our critical value is based on not only our confidence level, but our degrees of freedom. So I could just recalculate for the new value, and then I'll compare whether it's a narrower or wider margin of error. So I still have 95% confidence level, but now my degrees of freedom is 50 minus 1, which is 49. So let's find that new critical value. So we still have our 95% confidence level, but our degrees of freedom is instead 49. Now, we've got the choice between 40 and 50. You always choose the previous value if you don't have the exact value. So we'd be looking at 40. And thus our new confidence level is 2.021. So 2.021. Okay, my standard deviation of the sample is still 9.59, but now I've got the square root of 50 as opposed to the square root of 77. We'll type this into the calculator, round to 2 decimal places. Okay, that would round to 2.74. And we could see we're going to be both subtracting a larger number and adding a smaller number, which would give us a wider confidence interval. So as always, if you have questions, do feel free to contact me through our campus communication, and I'll be very happy to help you.